Lysine is one of the 20 amino acids that's used to make a protein within the human body. Just like any other amino acid, there's going to be essential carbon, or the alpha carbon, the chiral carbon, to which there are 4 different attachments. That's what makes it chiral. One of those things is a carboxylic acid, where you've got a carbon, 2 oxygens, and a hydrogen, or COOH group. You've also got an amino group, or a nitrogen with 3 hydrogens attached to it. This nitrogen should only have 2 hydrogens, 1 lone pair, and 1 bond to this carbon. So because it's carrying this extra hydrogen, this carries a +1 charge. That carbon's also going to just have a hydrogen attached to it, and then it's going to have an R group, and that's what makes every amino acid unique. In the case of lysine, this R group is going to be a bunch of carbons, and at the end there's going to be a nitrogen that again has 4 different attachments, 3 hydrogens, and then 1 to this center carbon. So this is also going to carry a +1 charge. So at the lowest pH, or where the environment has all kinds of hydrogens in it, this is going to have as many hydrogens as it can have. And at that point, you've got a +1 here and a +1 here. Everything else is 0. So this molecule is going to carry a +2 charge at its lowest pH. As you increase the pH or lose hydrogens from the environment, and so now this molecule needs its hydrogens less than the environment does, the first hydrogen that this molecule is going to donate comes from the carboxylic acid group, or the COOH group. And this happens at a pH of about 2.2. At this point, now this oxygen has an extra charge of -1 because it's got some extra electrons on it. And so now we've got a -1 here. This is still +1, and this is still +1. So -1 and +1 equal out to 0, and then this +1 gives it an overall charge of +1. This molecule is going to look like this until the pH gets to about 9.1, at which point one of the hydrogens that attach to this nitrogen is going to be lost, and it's going to gain back its lone pair. So now this has a -1 charge because of its lone pair. This has gone to 0, and this is still carrying its +1. And so because this is still carrying its +1, we've got a -1 here and a 0 here. This molecule overall is going to have a charge of 0, and that happens at about 9.1. It's going to lose from this nitrogen before it loses from this nitrogen, because all of these other carbons help to balance out the extra +1 charge this is carrying. Whereas here, this is a little bit more unstable because there's only 1 carbon that it's directly attached to that's helping balance out the charge. So this one's going to lose its hydrogen first at about 9.1. Then keep going up, losing the number of hydrogens that's in the environment, which means this molecule is going to need to give up more of its hydrogens. The final hydrogen is lost from that nitrogen on the R group at a pH of about 10.4. So at that point, you're going to have a 0 charge here, a 0 charge here, and a -1 charge here. So after a pH of about 10.4 or higher, this overall molecule is going to carry a charge of -1. The pH of the human body is about 7.4, which is known as the physiologic pH. And at that point, the nitrogen is still attached to an extra hydrogen here, as well as this nitrogen is still attached to its extra hydrogen. So this is going to carry a +1 charge, and this is going to carry a +1 charge, and this is only carrying a -1 charge. So you've got +2 and -1. At physiologic pH, this molecule is going to carry an overall +1 charge. The thing that really makes lysine its own individual amino acid is the R group. So let's just talk R group. This R group has 4 carbons with a whole bunch of hydrogens, and then 1 nitrogen that has even more hydrogens. This has a lot of nonpolar bonds. These carbon and hydrogens are all nonpolar bonds. But anywhere nitrogen is involved, you've got some kind of polarity going on, because nitrogen is going to want to hog electrons a lot more than any other element. And so this is a polar bond, this is polar, this is polar, and this is polar. So this is considered a polar amino acid. Beyond that, Because this nitrogen actually has a formal charge of +1, this molecule is considered basic. So yes, it is polar. There are polar bonds that can do hydrogen bonding with other molecules. But even more importantly than that, there's a lack of electrons on this nitrogen and it needs them back. So it's going to have an actual charge of +1 and be basic. Lysine is another one of those amino acids that is essential. Your body's not about to make lysine. Anything where there's extra nitrogen, your body's not trying to consume more nitrogen, it's trying to get rid of nitrogen. So lysine is not something that your human body makes. You have to eat it for it to show up in your proteins. And one of the unique things about lysine is that it can be converted into acetyl-CoA, which can then go on to make more fatty acids. So this is also considered a ketogenic amino acid, or it's able to make ketones, which eventually become fatty acids. Because of this actual formal charge on this lysine, your body is able to take advantage of the fact that it can create an ionic bond, which is the strongest bond that your human body can make. And it's going to be able to do cross-bridging. So if you've got lysine on one protein strand, which is carrying this +1 charge, and then you've got another strand that's going to carry a -1 charge, that -1 and +1 can bind together. And now you've got something called cross-linking. Another way your human body can take advantage of the fact that this has an actual +1 charge is in histones. Your DNA structure, the backbone of the DNA, has a -1 charge. And so this +1 charge is going to go straight to that -1 charge on the phosphate of the backbone of the DNA. And it's going to also make an ionic bond. And that is one of the most important factors that helps histones, which are made up of amino acids because it's a protein too, bind to DNA molecules. When histones are bound really, really tightly to the DNA molecule, that DNA can't be accessed in order to make transcription happen, in order to make other proteins. So anytime you have histone bound really, really tightly to DNA, that's going to be DNA that's not used to make protein. But one thing that can happen is you can change the way a histone is structured. You can add an acetyl group where you've got a CH3, another carbon that's double bonded to an oxygen, and then bound to a hydrogen. This hydrogen can detach. This acetyl group can bind to that nitrogen here. And now this nitrogen is not as easily accessible because it's been acetylated, or acetyl group has been added to it. And because it's no longer easily accessible for that positive charge, it's going to detach from the DNA. And that's going to allow the DNA to be accessed for transcription to happen. So one of the ways your body can regulate transcription is by adding an acetyl group or acetylating lysine. And when it's acetylated, this lysine can't bind to the DNA, which means the DNA can do transcription. If this acetyl group is not attached to this lysine and it's carrying this extra hydrogen, then this nitrogen can bind directly to the DNA and prevent transcription from happening. So lysine is heavily involved in the regulation of DNA transcription. The addition or removal of the acetyl group is one of the epigenetic modifications that can happen over time.